Hello everyone, we are starting a free open lecture on our Discord. All our lectures are held weekly, without interruptions. If you, the viewer, want to ask questions and get answers online, join our lectures. You can find the link to Discord in our Telegram channel. To find out the lecture times and stay updated with all the latest announcements, join our Telegram channel. It's the best way to ensure you never miss any important information. So, now the most important thing we need to discuss is the most delicious part of this task is that every time I open these two functions, union and join, it's hard to understand right away what's going on. So, to start with, we have path coloring in profile B. What does that mean? We look at the profile A for the highest path number that is occupied, update it, and then we get all the transitions in array B in ascending order, meaning everything except 0 is numbered in ascending order. We increase the count, send the count if there is a transition in this and that column TFSP. Then we proceed with the actual check. We have a counter K, which verifies. To elaborate, when we look at profile A, we are specifically identifying the highest path number that is currently occupied and making necessary updates to it. Following this, we gather all the transitions present in array B and arrange them in ascending order, ensuring that every element except for 0 is numbered sequentially. We then increment the count and send it if there is a transition in the specified columns of TFSP. Finally, we move on to the actual verification process, where we utilize a counter, referred to as K, to perform the necessary checks and validations. Do you want to become a fantastic programmer? Subscribe to our Telegram channel. We definitely have something like more content for you. A cell, and we can enter it either from the left, meaning somewhere around here we had a transition right here, or over here. And then the path goes along the line. And we can enter from here to the left. We can enter from the top. That is, the transition from A is from the top. We can enter from the bottom. Accordingly, we definitely need to understand if there's any kind of mess happening here. For example, we can't have something coming in from 3 sides at once. Indeed, well, because we won't be able to, in this particular sense, we ultimately end up in a situation where first you go there, then you come back, meaning that the convergence breaks down in this specific situation. We need to have only 2 entries or even just one single entry, meaning that if we have 0 entries, it turns out that the current cell is empty and we haven't used it, which means we can't get such a result. Well, it's clear that the laws of Komi-Vejora will definitely be broken accordingly. So we have possible transitions either like this or like that. So we just go straight down through TFSP. We can go further along, or we can go based on the situation at hand. This thing will now be thoroughly checked using the counter K, meaning we check the transition from A, the transition from B, and the transition from left, and the number of transitions to the current cell is summed up. If K is exactly 0 or 3, then return join. Join is false by default, meaning such a transition is not possible. If exactly one path enters the cell, we determine its color. The color will be able to immediately sum up the transition from here, here, and here, because 2 out of 3 of these colors will be 0. Accordingly, from the sums, we will simply get the color from where we came. If we have 2 transitions, then we recolor either B to the color of A. This process is crucial for ensuring the accuracy of the transitions and maintaining the integrity of the system. Additionally, it is important to note that the transitions must be carefully monitored to avoid any discrepancies. Therefore, we must be diligent in our checks and balances to ensure everything is functioning as expected. This thorough approach helps in identifying any potential issues early on and allows for timely corrections. That is, if we still have a transition happening such that we went like this and entered here, we have some color A and there will be color B. They need to be painted in one color. If we recolor BF, If we entered this scenario, if left equals 0, instead of any other value, then it results in a through transition, a change. Only in this specific case do we color it like so. TFSP here A, and here A should be colored accordingly. Further, if we entered from the left side specifically, we essentially recolor what happens right over here. This means that we've pulled it somewhere from the left side and end up recoloring what was already there. It turns out that when we transition from somewhere here, which could be any point in our current state, we go either this way, which might be a positive direction, or that way, which could be a negative direction, and in all these cases, the flowers need to be the same color and type to maintain consistency. Meanwhile, we might get a false value here, indicating an error or inconsistency, which means we are trying to create a cycle, that is, this kind of repetitive loop, while we still have potential paths or alternative routes that can prevent us from making this cycle. In other words, if there is another event or occurrence taking place in that location, we currently do not possess the authority or permission to initiate or commence this particular cycle or process. Anya, we cannot do this if we have something either here or there, I don't exactly remember, but basically the check will be whether we can do it or not. If we cannot, then we will need to find an alternative solution or approach to address the issue at hand. Additionally, we will need to consider other options and strategies to ensure that we can effectively manage the situation. In principle, we cannot do the join. It will ultimately return chaos, essentially. And then at the end of all these passages, if we have some entry left somewhere to the right, left or right, it is the same. But I think it's clear why, if we have passed through all such cells completely, we have one cell left, and it goes somewhere to the left. And where? If everything is already finished, we need to either turn here or there. Therefore, this cannot be done. It will be false, and this is important to note. Next, profile normalization occurs here, which is a crucial step. What does that mean? Let's explore further to understand it better. While we were changing color of B to A, in fact, the numbering of B could have been too large, meaning it could have started not from 1, but from 2, 3, or something else like that, in order to reduce the numbering. We recolor using the passive C, precisely passing through, if we have a transition occurring. By carefully and accurately ensuring that each step is followed, the process of recoloring becomes more efficient. We increase the path number and pass K, otherwise we pass the color that was passed to the other end with the same color. So, how does this happen? If we had a path with color 4 here, and another path with color 4 here, and when we entered here, a maximum of 2 colors had been used. We increase the path number and pass K, otherwise we pass the color that was passed to the other end with the same color. So how does this happen? If we had a path with color 4 here, and another path with color 4 here, and when we entered here, a maximum of 2 colors had been used. I know that we can easily and effectively recolor this number 4 to a number 3, which is a simple and straightforward process. Accordingly, as a result, we recalled that for the next 4, we should also recolor it to 3 in the future. Accordingly, when we get here, we will automatically recolor it to 3. There may still be a used number of colors here, but we will recolor it to 3 anyway. Want to become a great programmer? Subscribe to our Telegram channel